right, well, good morning, everybody. My name is Linchangco, as you've kind of heard. And after hearing about all that great success, I want to talk about failure. So, failure is really scary, especially if you are starting a new endeavor, say graduating with a PhD and looking for a job. It's even scarier when you're going to go into a field or go into a company that is kind of a startup or just beginning. And the biggest thing that I've learned I've only been there for about 8 months at this point, but the biggest thing I've learned has been to not fear failure, but to acknowledge it. And the reason you want to acknowledge it, not fear it, is because that's where you can learn. That's where opportunity comes from. That's where innovation starts. Is you try, you build, you break, but then you have to look at it, learn from it. Then you have to refine your hypothesis, refine everything that you're doing, and just keep iterating over it and try again. And I think that's embodied really well from a quote from Thomas Edison, who everybody knows invented the light bulb. And he said that I have not failed. I've just found 10,000 ways that won't work. You just got to keep going for that 10,001th way to make that your idea or your vision, your dream come true. And with that, I want to kind of talk about all the failures I've already had at the company. So one of the most amazing things that I've been able to do is work with a dedicated different individual team that's been able to teach me a lot of different things and show me a lot of different fields. Oh, should I just hold it? I can hold it. So I'm very soft-spoken sometimes, so you have to hear me a little bit louder. I try and project, but it doesn't work. So the coolest thing about working at 25-2 is that Kim and Eric and everybody there, they're scientists. They get it, right? Failure is not something that that's foreign to scientists. Experiments fail all the time. Papers don't work out. In the wet lab, things don't work. You break computers when you're trying to do analyses. We've burned up quite a few of those already, doing a lot of our automated phenotyping. But it's the ability to be allowed to fail. So we don't make it a goal to fail. It's definitely not good, because then you burn through a lot of money and resources and time and energy. But it's those moments where you actually need to burn your time and your energy and work with a group of individuals that'll actually help you get to that solution. So with that, I want to actually discuss first failure. And the first failure we had was in our automated indoor phenotyping camera array system. And with that, there's a whole plethora of things that I didn't know coming into it. A lot of my formal education and a lot of the research that I did was in knowledge-based discovery, text mining, that sort of thing. Here I'm actually working with hardware. I've built computers before, but at this point in time, it's become easy enough where you can't really mess it up. But when you're trying to do something new, something innovative, something that hasn't been done before, it's all bets are off, right? So, but coming from the PEP program and kind of being faced with all these different types of adversity and being thrown into different things that you're not always quite ready for, like handling a group of four to five undergraduates or master's interns that you've never really learned how to lead a lab or do any of that, you get kind of numb to the idea of surprise, and you're able to just kind of overcome whatever it is that you have to do. You come up with a solution because you have to, right? And I'll start with, I guess, what the point of one of these are. So this is the Hawkeye Camera Ray, and we use these in indoor environments in order to monitor different types of things in crops. Well, really in seedlings for the most part. So a lot of times when you're doing plantings of different crops, you start in a greenhouse in order to get the crops grown up in a safer environment so that they can be more viable once you actually take them out into the farm or out into the field. But there's a lot of different things that can occur within these indoor environments where there could be a pest that comes in, or there could be something just mechanically wrong with some of the sprayers for watering or for an insecticide, that type of thing. You wouldn't really know what was going on unless you're monitoring it. And it's a lot easier to have an array of 24 cameras along the entire greenhouse than having somebody walking around and trying to guess, well, it looks like there's a dry spot over there, I don't really know why. It helps you to more quickly and more efficiently take care of problems that arise. And this was a completely new technology that was dreamt up, and I'd never worked with this type of hardware before, but you learn really quickly what it can and can't do, and then you try and make it do what it can't do. So we spent a lot of energy, a lot of resources, a lot of manpower going to, it was dreamt up, it was built, and then we tested a little bit in our facility, but then we just said, you know what, the only way you're going to learn something is if you take it out into the field and actually stress test it. So we immediately went to a greenhouse all the way down in Florida, in Okeechobee, and we spent quite a few weeks there, not consecutively, mind you. We had to go back and forth in order to actually get things to work. So we ran into a whole plethora of different issues, starting with power supplies, how to actually wire the power supplies, all the different networking issues in terms of these are all connected wirelessly to a local server in the greenhouse. We had to work on all of that and come up with a system or a solution, because a lot of the times greenhouses or places that these are going to be used, this camera array is going to be used, that they don't have a lot of bandwidth, right? It's in the middle of nowhere. Idaho, I guess you have some, there's a lot of research out there, so they have fiber, so that's not a big problem for Idaho. But in most places, in Okeechobee, Florida, they had basically your mobile broadband, and that was the speed that you're able to use. So each of these cameras, you can see, let's see, there's a pointer. Each of these cameras have 3 different cameras actually built into them. So each of these images that are being taken of all the seedlings and the plants in the greenhouse are, I don't know, roughly anywhere from 5 to 7 megabytes each, and they're all in raw format. But the thing is, when you're taking 24 images across 3 cameras, across different time series points, you very, very quickly run into your big data problem, right? And it's not even the problem of actually analyzing it just yet. It's the problem of how do you get a large data set from one place to another. Currently, the quickest way is still UPS, right? You just send a hard drive of data. But we came up with a series of different solutions. That local server was actually the first part of that solution in order to allow a place to aggregate all that data so that we could then get it up to our servers in Minneapolis and actually perform all the different analyses that we needed to do with the images we're getting from the greenhouse cameras. So this was, it was discouraging at some points in time. When you're going down there, you thought that was the last trip, something goes wrong, you have to go back and come up with a solution for something like the power again, or it's in a very humid environment, so we have to modify the cameras in order to actually have something like a fan in there to actually keep them cool, especially when they're at the top of the greenhouse is what gets up to, I don't know, 180 degrees Fahrenheit. But all in all, from all the different failures that we accumulated, we're able to get the system working, and at this point we have it in multiple locations, and it's actually running really, really well. And I just wanted to show you guys some of the imagery that comes out of it. So here on the left side, you'll see a bunch of different trays, basically, worth of seedlings. And each of these trays is, I don't know, I want to say 200, maybe 800? Oh, okay, yeah, there's a ton of seeds in there and a ton of plants, right? You can only imagine. But if you see on the right here, so this is an RGB image, the same kind of image you would see if you took a picture with your cell phone. Lets in all the bands of light. But over here on the right-hand side, you can see all these little red dots, right? And all these little red dots are covering all the little green dots that are actually in this RGB image. Each of those little dots is a seedling. So from being able to actually set up the camera array, we're actually able to get all this data now where we're able to count and size all the different little seedlings that are in each of these greenhouses, and we can monitor each one individually as opposed to just having a very general idea of different areas in the greenhouse. So this is another stage of that greenhouse. So this is, again, we were taking a lot of different time series images over a course of weeks. And here you can see that they've grown up and they've actually filled out quite a bit, all the different seedlings. But with a lot of the computer vision technology that we're doing and all the algorithms that we're actually employing in our JACE machine, we're able to continue to identify each individual plantlet in the actual greenhouse so that we can use that to monitor the health of the plants and the health of the greenhouse in general and be more efficient. So that was the first, one of the first forays I had into 25.2 and a lot of the technology that we were working on and trying to develop and build and innovate. And one of the big things is in machine learning or artificial intelligence, whatever you want to call it these days, the best way to train a model or to teach a model is to get data, and to get data quickly and efficiently. Eric was talking earlier about how he was going through and building these greenhouses in Idaho in order to inoculate all these different plants, all these different varieties, and trying to understand which ones are good. But a lot of that he had to do by hand. He had to look at each one individually. Same thing when you actually go into a field at that point, right? If anything, it actually extrapolates your problem because now you're covering multiple acres worth of plants that you have to go through, look at, phenotype, and collect data on. So one of the things that Eric came to me with was the fact that we needed to be able to do that very quickly and very efficiently, and we just can't do that as people, or it costs too much to hire a bunch of people to go through a field and do that. So that's where I introduce the drone. So drones are synonymous with recreation today. I'm sure everybody has seen DJI drones and that kind of thing that are flying around, just taking video and seeing what you can see. But our drones are built with a very specific purpose, and that purpose is to collect in a very efficient and automated way the different types of phenotypes that we can garner from the field. So it's the idea of the greenhouse camera array, but to cover massive amounts of acreage. And this was a huge problem in itself. When we started out, we were using these, I don't have my phone with me, but we were using DJI drones to start out with and kind of test and play with. They were massive. You had to always check it because the case for it was a hard case, like a military-style case, about this big, about this wide. And you always have to check it if you have to go fly somewhere because, let's face it, you have to fly somewhere if you're going to go look at a field and phenotype a field, right? It's not in your backyard. So it's very cumbersome. The batteries are all very expensive and very proprietary. You're not able to do any workarounds to actually make them last longer. You have to use at least two batteries just to cover about 3 or 4 acres. It just wasn't working. It wasn't going to do anything that we needed to do in any amount of time that we needed to do it in. So, so Eric bought a drone company. But this drone company was really, really interesting. It was fascinating. You can see right here, this drone is 3D printed. All the pieces of it aside from the electrical components. This looks nothing like what the drone looks like today. This was one of the first iterations of the drone. And I'll actually show you guys in a second here. This is the drone now. It's in this tiny bag that you can put in your back. You can, we fly a lot to go test them out, so we actually just put it in as our carry-ons and put it underneath our seats on the planes. So the hard part about this is I don't think there are a lot of drone companies doing agriculture, DJI included, because it's so difficult. The the optics of it. Eric talked about Dr. Emilio Hernandez. He is an amazing individual. He came from Mexico, and he came to the U.S. and he got his PhD in nuclear computational engineering. Beyond me. So he does a lot of modeling. He understands a lot of that, but we also really rely on a lot of his physics understanding. So the physics of optics, right? So cameras, lenses, light refraction, all of that falls under his realm. And the hard part, again, is not dealing with a lot of the software. Sometimes it's the hardware. So with the hardware, once the company came in and we had the drones, again, I said we had to change it completely. It's not that it wasn't working, it just wasn't working efficiently and it wasn't working for the purpose that it needed to be purposed for. So I actually spent another week down in Florida with Armillo. This was probably our third or fourth time down there, separately from the camera arrays, working on drones. Again, I have never worked on drones in my life. Really cool, I'll say that. But a whole different thing to understand. But a lot of the learnings you get from one section goes to another. So the camera information that we were working on there actually helped to better understand how we can work on drones as well, and how we can actually capture all this phenotypic data quickly and efficiently. So we went down for the last time to finish this, and Armillo and I were there working on it 8 a.m. to 1 a.m. every day. We thought we would be like, we can do this. We got there Sunday, we'll be fine, we'll get it done by Wednesday. A lot of sleepless nights. A lot of times where we thought, let's just sleep on the floor of this office. That way we can just wake up really quickly and then keep working. I had a flight to go back on Wednesday, canceled it. Another flight Thursday, canceled it. Again, a lot of time and resources used in order to overcome a lot of the failures, right? But finally, on Saturday, we got it up and running. And this was actually that first flight. Right. So now we actually work with a partner with our drone company. It's Crop Search, and Rob Nupp is actually here representing Crop Search today. They've been very, very helpful in giving us feedback on how to use the drones and how they're actually going to be using the drones for crop scouting out in the different fields. And at this point, it's not just that we can fly drones and take pictures, because let's face it, that's actually not too difficult. It's the ability now to actually take those images and analyze them. There are a lot of different companies out there right now that are trying to do this, but they can't. And that reason is because they don't have Dr. Emilio Hernandez. So Dr. Hernandez was able to create a stitching algorithm that is capable of stitching together multiple photos. So all these photos I was telling you again, as I do this, I'll show and tell. Each of the drones is similar to, this one's bright orange, or yellow, sorry. Each of the drones is similar to the Hawkeye Camera Ray. And you can see there are actually 3 different camera lenses on the bottom of the drones. And with that, we do that in order to capture multiple different spectral bands of light, so we can actually do different types of analyses. You have your RGB camera, which is going to be the same thing as your cell phone camera in terms of what's let in. Then you have a blue bandpass filter and a red bandpass filter. This image is actually a blue bandpass filter, which is filtering out all the different blue light that's coming into one of these cameras. So I'll actually just pop this right here so you can take a look at it. But the problem is everybody that's out there right now that's actually trying to stitch these images together, they do what's called blending of the pixels. And when they blend the pixels, you actually lose a lot of different data points. You're not able to actually garner all the information that you would need because they're actually just blending a lot of the picture together. You're losing a lot of the detail that's actually coming out from the phenotypic data. And we wanted to show you guys this. This is a small portion of a giant geo-rectified orthomosaic, which is just the giant stitched image that's actually placed geographically in the location that it belongs. And this is actually the oat fields, or the oat trials that we have in Idaho right now. And we wanted to just showcase what we're able to do with not just the stitching portion of it, but actually how we can actually analyze the data and garner information from that. And here you can see we have plot A right up here and plot D. So even just by visually inspecting that, you can see there's a pretty big difference between those two plots. And the data definitely backs that hypothesis as well. So on the first image up here, you can see we're able to actually count and size all the different plants within that plot. And this can happen not just in oat, but in multiple different crops as well, like potatoes and cabbage, and actually even in larger trees like citrus. And you can actually see here there's this little square boxes from all the computer vision that we've been using in order to actually identify each of the individual plants, as well as how large they are in relation to one another. And it's very clear to see that there are quite a few more plants in plot A than plot D here, as shown through the number of different plants here. That's useful in accordance with the rest of these different phenotypic traits, like soil health and canopy, your nitrogen, and your canopy closure, to allow you to understand something like yield, like how many of the plants are actually coming up that you expect to come up. And these types of things also tell you, like nitrogen density, that'll tell you the soil health and what you actually need to add to the different plots in order to get them to grow better, or what they're deficient in. We're actually also able to do moisture as well in the soil. So from that, you can actually garner all that phenotypic information very, very quickly. And the whole point of that is to combine it with the other nodes in our knowledge base. And by doing that, we're able to combine all the phenotypic data with genotypic data, as well as with all the public knowledge that's out there through text mining, in order to come up with a way to rapidly or quickly understand what we need to do in order to breed new crops to feed the world. And I wanted to take a quick sidebar to actually talk about another tool that we created. And this was in response to one of our small fruit partners out on the West Coast. And the problem they had was that there is a latent pest that was actually in the soil there called Fusarium. So this was in their strawberry fields. And the problem with Fusarium, it's kind of stepwise, really. It's kind of a 1 or 0. If it's infected with Fusarium, a lot of the times those crops will just die. It's either they're dead or they're alive. But there is a bit of a spectrum, a continuous spectrum, in terms of the severity of the disease from that Fusarium pest. But the problem was that in California, there's not a lot of water, right? They're always having issues with water and how much they can actually use for drinking, or even just to irrigate their fields. And the thing is that when they're going through and when breeders are going through and trying to make these different selections for something that's going to be resistant to a pest like this, they kind of have to use a lot of statistics in terms of just saying, let me just use the biggest number of crosses, the biggest number of varieties, to try and find something that's actually going to be resistant. And that's very wasteful, it's very inefficient, and it's not really that sustainable. Because not only do they have to plant the seedlings in the greenhouses, but then they have to transplant those seedlings into the actual fields. And then from those fields, they have to transplant at least one other time, the ones that they actually do want to keep that have shown that they are resistant to whatever phenotype or trait that they're looking for. And they're losing a lot of water, they're losing a lot of resources to this pest. And they'd already tried traditional breeding and their single marker assisted breeding as well, to try and understand, well, what's the quickest way we can turn this around, because we're losing everything that we're trying to plant. And we're able to create predictive analytic models that combine a lot of the phenotyping that we're already doing, automated phenotyping, with the public information that's coming back from a lot of different literature and all the different seed repositories that Eric was talking about earlier, along with genotypic information that we're gaining in our wet lab. And in doing that, we're able to not only impute scores in terms of resistance to something like Fusarium, we're able to actually select and create hypothetical crosses between all of them so that we'd know right away whether or not different crosses would produce Fusarium-resistant lines. And in doing so, we had to create a culling selection tool. The whole idea is that we create an assay to actually be able to test for Fusarium resistance. After that, we weren't able to, at this point in time, scale to do all the genotyping, so we handed that service off to a larger company, LGC. But the problem with that is that they're all the way, the largest facility that we use is in England, in the UK. And there's a lot of customs issues when you're trying to send samples between different countries. But all that aside, the genotyping takes the longest. We're on a very, very tight schedule when they begin to actually create these seedlings. Once they make these crosses, make these seedlings, they send samples, we genotype them, but then they need it within a month or less back in order to actually call out the ones that they don't need, the ones that they're actually going to keep, and transplant into the fields. The big problem with that is it takes them, I don't know, maybe a week to sample. It takes LGC at least 3 weeks in order to do all the genotyping and then get all the data back. So that leaves us with a day to run it through our models, compute scores, and then also visualize the data, but not just visualize the data, but make it in a way that's going to be easy for anybody, especially a breeder, in order to actually use and make decisions on that data. So what we came up with was a simple slider tool. I think this makes sense to everybody, right? You take one end, the low end. So there's a arbitrary score here for Fusarium, and from that score, you have a range where you can move the slider to say, well, I want to be able to keep all the lines that are going to be resistant to Fusarium, and I know that they are based on X cutoff. So all you have to do is move the slider. So here we'll set it at something like 7.38, which is pretty high. That way you're going to call all your non-resistant lines, but you're going to keep all your resistant lines for Fusarium. And after that, it'll give you a data output here, which will actually show you your percentage of all the different lines you're actually going to keep from all those seedlings. So with that, our partner used this, and they called 50% of their entire program, which started at 150,000 different seedlings, and they cut it down to 75,000 different seedlings. And in doing so, they planted them, and they're actually seeing that all the resistance is actually there that was predicted, and barely any, if any, of the susceptibles actually got through. So all the lines that they have now are actually Fusarium resistant at this point, across not just one program, but across, I think it was like 8 or more programs. They keep adding on to it. So, but that alone saved them, I don't know, millions and millions of dollars just in terms of their resources for water, for labor. But at the same time, this is a really good showcase to say, well, the machine works, right? You feed it enough data, you feed it enough good data coming from automated phenotype collection, coming from a lot of the genotypic data that we're getting from our wet lab. And you can come up with something that works, that's accurate, that works in biology. That'll actually allow you to say, well, I don't have 30 years to develop a new variety to feed the world. I have 3 years. You can do that now. And to kind of teeter off here at the end of the program, oh, forgot about this one. So this is, you can actually also download a lot of the information right here from the culling tool. And this will actually just give you a quick little printout of what it is that it's for each individual little cell. But when you go through and do anything in the wet lab, it's always 8 by 12 96 well plates. That is not what they had in their planting greenhouses, of course. So there's a lot of translation between where different seedlings go and being able to keep track of where they actually are, but also then translating where they are in space as well, so that you can just automatically, in a very, very quick way, just say, here's the tray that you guys have. The red ones take out, the green ones are the ones you're going to keep. Those are the ones you're going to move on. So that cut down a lot of their time for that 4-week period where they only had so much time to grow the seedlings, cull the seedlings, and get them back in the ground. But with tools like that, we're able to create new technologies again and continue to innovate into something called the crop crate. And we're actually partnering with Vindara to bring this to life. And Vindara is actually represented today by Jade and Rusty over here. With that, we're able to, in an automated way, monitor all the plants that are growing in these little crop crates. But at the same time, they're set to different schedules. You can, we're building an app to allow you to set different schedules for the light regimes, for the watering regimes. It's a hydroponic, aeroponic mixture in order to actually grow all these different types of, to start with leafy greens like lettuce and basil. And with that, now we can actually take the power of experimenting out of the scientists' hands, out of the breeders' hands, and now we can actually make, 3,000 different experiments across all different places in a controlled environment in one of these crop crates. We can put them in schools and they can understand how to actually use them. We can put them in every kitchen and understand, well, we want to know which varieties are actually good, which ones are going to have the properties or the traits that people desire. And people can actually tell us, and we can actually get all that data back to understand and be able to give the power of breeding to the hands of everybody else, or all the common people, or everybody that's not a breeder, right? And that's how you try and feed 9 billion people, right? Thank you.